We're going to walk through an example where we're going to find the critical point or points of the following nonlinear autonomous system, and then we're going to classify the type and stability of each point. Our nonlinear system is dx dt is equal to x minus y, and dy dt is x squared minus y. The first thing that we need to do is find all the critical points. To do that, we're going to take the derivatives dx dt and dy dt, and we'll set those equal to 0. This gives us 0 is equal to x minus y, and then we have 0 is equal to x squared minus y. In this first equation, I am going to let y be equal to x, and then we'll plug that into our second equation. This gives us 0 is equal to x squared minus x. We can factor out an x. And from here, we can see that we get x is equal to 0 and x is equal to 1. Since x is equal to y, our critical points are going to equal 0, 0 and 1, 1. In step 2, we need to find the Jacobian matrix. I put the formula for the Jacobian matrix over here on the right. Let's begin by writing down what f and g are. Let's pull this back down. F of xy is what dx dt is equal to, and that is x minus y. And then g of x and y is what dy dt is equal to, and that is x squared minus y. Now we can take our partial derivatives and put them in our Jacobian matrix. J of xy is equal to, the first partial derivative looking over here on the right is df dx, and that is going to be 1. And then we take df dy, and that is minus 1. dg dx is going to be 2x, so we do have a variable down in there. And then dg dy is minus 1. Let's take this Jacobian and let's bring this over to our next page. In our last step, step 3, we are going to evaluate the Jacobian matrix at each critical point. So let's go ahead and let's put down what our critical points are. They were 0, 0 and 1, 1. And then for each of these critical points, we're going to find the eigenvalues and then classify the point. Let's work with the critical point 0, 0 first. The Jacobian evaluated at the point 0, 0 is going to be equal to 1 minus 1, 0 minus 1. We'll call this matrix matrix A, and we can use the characteristic equation lambda squared minus the trace of matrix A, I'll show you what that is in just a second, plus the determinant of A is equal to 0. This gives us lambda squared minus the trace of A. To find the trace of A, all you do is you look at the main diagonal elements and you add them. So this is going to be 1 minus 1, so we'll get a 0. And then the determinant is the main diagonal entries multiplied, so that's minus 1, minus the off diagonal entry multiplied, and that's 0. This gives us lambda squared minus 1 is equal to 0. So we have lambda squared is equal to 1, and this gives us that lambda is plus or minus 1. We're going to need this in a minute, so I want to highlight this. And then beside this, I am going to put that these eigenvalues correspond to the critical point 0, 0. Now we're going to do the same thing, but now we have a critical point of 1, 1. So we evaluate the Jacobian at 1, 1. This is equal to 1 minus 1, 2 minus 1. Our characteristic equation is lambda squared minus the trace. The trace, again, is equal to 0. So we have 0 times lambda. And then we have the determinant, which is minus 1 minus the negative 2, so that's plus 2 is equal to 0. This is lambda squared plus 1 is equal to 0. So we have lambda squared is equal to minus 1. And that gives us the eigenvalues lambda is plus or minus I. We'll highlight that. And then let's put that these eigenvalues correspond to the critical point 1, 1. Now we need to classify these 2 points. I have a chart here that's going to help us do that. Let's look up here at the top. Our eigenvalues are plus or minus 1. Those eigenvalues are real and they have opposite sign. That's found right down here in our table. And this means that our critical point is going to be a saddle point and it's going to be unstable. Let's now look at our next set of eigenvalues. They are complex and there is no real part, so they are purely imaginary. Down here is where we have purely imaginary, and that tells us that our critical point 1, 1 is a center and it's stable. Let me summarize this here because this is going to be our answer. 0, 0 is an unstable saddle point. And then our critical point 1, 1 is called a stable center. Looking over here at the diagram on the right, you can see in the same phase plane, we have 2 very different behaviors. This graph lists both of the behaviors separately, and I did that on purpose because I wanted you to see both of these individually. The actual phase portrait is a combination of these solution curves. Near the critical point 0, 0, solutions move away from the saddle point, and near the critical point 1, 1, solutions orbit in closed loops. This is exactly why we need linearization. A single global matrix A would never capture both of these. You need the local Jacobian at each critical point to tell the full story. And that's it. You now know how to linearize a nonlinear autonomous system and find and classify its critical points. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.